Hello, everyone. My name is Emily Wenger, and I'm here today with my colleague Sean Chan to talk to you about our system, Fawkes, which is designed to protect individual privacy against unauthorized deep learning models. Recently, it has become quite easy for anyone to train a fairly effective facial recognition model. Research advances have shortened training times for big models. Hardware continues to become cheaper and faster, and social media provides a plethora of labeled training data. Together, this means that really anyone with some coding knowledge and a nice enough computer can train a fairly powerful facial recognition model. Well, this is interesting. It leads to a very concerning question, which is, what if the wrong kind of people take advantage of this new accessibility? For example, I have a lot of fairly personal images posted to my various social media accounts, pictures of me with family or in regalia from the University of Chicago, that kind of thing. What if someone were to scrape those images and use them without my knowledge or consent to train a facial recognition model that recognizes me? Then I could just be sitting on a Zoom call, as I do often these days, and someone could come by and take a screenshot of me and upload it to that Face ID service that has the model trained in my social media photos. The Face ID service could match the screenshot easily to my other photos and yield some pretty personal information to the person who looked me up. For example, if they saw this picture, they might know where I live or go to school, which could help a stalker find me more easily. This picture could give them info about my grandparents, which could help them construct an elaborate phishing or extortion scheme. Knowing about my relationship status could lead to negative employment decisions. And depending on who you are or where you're from, this kind of aggregated personal information presented by this collection of photos could lead to discrimination or oppression in a variety of forms. Obviously, this is hugely problematic. This kind of tracker-esque Big Brother scenario seems really kind of futuristic and scary. And it's actually also real. Clearview.ai is a company that does exactly what we discussed. It was first reported on by Kashmir Hill of the New York Times in early 2020. Clearview, like we said, collects all these social media photos without people's consent or knowledge and builds a big facial recognition model that it offers to people who subscribe to its services. Those subscribers can then upload a photo of someone they're interested in and receive back matching photos of that same person and a lot of other personal information that Clearview has aggregated. The customer list of Clearview is not public, but the New York Times article noted that it at least includes some government agencies, law enforcement departments, and even private citizens who can afford to pay Clearview's fees. The existence of Clearview.ai is terrifying. Individuals need recourse to be able to guard themselves against this kind of intrusion of their privacy. And that is where our system Fawkes comes in. Fawkes is designed to help individuals fight unwanted facial recognition. It protects images in specific ways so that when those images are shared on social media, they can't be used to train a facial recognition model that recognizes you. In this talk, we're going to discuss how Fawkes is designed and evaluate its performance. Before we do that, though, let's just quickly look at the goals and assumptions of Fawkes. We consider two parties in our system design, a user and a tracker. The user is a pretty ordinary guy and has just some limited computational resources and access to a well-trained feature extractor, which we will discuss shortly. Together, the user uses these tools to protect or cloak their images in Fawkes terminology before posting them to social media sites and other places online. On the other end, the tracker, like Clearview, can scrape those protected images and use their extensive computational resources in an attempt to train an effective facial recognition model. Note that the tracker really only has access to these protected images. Before we dive into how Fawkes actually protects images, let's just briefly review how facial recognition models work. To train a facial recognition model, you need to first collect a large data set. In this example, we have 4 different classes in that data set. And you use those to iteratively optimize what's known as a feature extractor in order to produce a well-separated, quote unquote, feature representation space. The feature representation space is just a mathematical understanding of how the model separates these different classes. But as we can see in the bottom figure, this model has learned to easily place each of the 4 classes into distinct regions of feature space. So that means when a new image of, for example, me is presented to the model, it is mapped to the region that the model understands to be associated with me, and so is classified as me. In order to do its protection work, Fawkes kind of manipulates how the feature representation space of the model looks, which confuses the model and helps individuals evade unwanted facial recognition. So on the left, we see just the feature space of a normal model trained on normal photos, and we can see that it's well separated and well delineated. And on the right, this is a model trained on quote unquote cloaked images of me, where my feature representation has been shifted towards that of Beyonce. So the model no longer has a distinct region associated with me. Then when a normal image of me is presented to that original model, it can easily identify as me because I'm mapped to the space associated with me. But when that same original image is presented to the cloaked model, it's mapped to Ben's feature space. So the model really can't recognize me. And that is how Fawkes provides that protection for individuals. My colleague Sean is now going to provide some additional insight into how Fawkes works and how it performs.
All right, thanks, Emily. The way we compute the perturbation for an image is a very standard optimization technique. The goal here is to mimic the feature space representation of target faces. And we have a constraint to make sure the perturbation is indistinguishable by humans. That is why the main objective here is to minimize the L2 distance between the 2 representations. And the constraint term here is to control the amount of modification we added to the image. We use DSSAM to measure the amount of perturbation. It is an objective measure of image distortion and is often used in the vision domain. Next, I will present the experiment results showing Fawkes is effective under different conditions from the baseline to real-world settings. We'll start with the baseline, where we assume the user knows the exact feature extractor used by the tracker. As we have discussed, the user is sharing some image of herself on the internet, and she cloaked her image using a feature extractor. So the tracker scrapes the cloaked image from online, use the exact same feature extractor to train a face recognition model. We measure the effectiveness of Fawkes in terms of protection success rate, which is the percentage of real user image misclassified by the tracker's model. Here's the results of the baseline condition. We tested 4 different feature extractors trained using different dataset and model architectures. The protection success rate is 100% for each of these extractors. Next, we consider Fawkes in more realistic conditions. We leverage the transferability of feature extraction. Transferability is the observation that the perturbation can transfer to different feature extractors and have a similar effect. In the case where user has no information of tracker's model, whether the tracker trained using a different feature extractor or train a model completely from scratch, our protection success rate is above 95%. Next, we test Fawkes against several real-world state-of-art recognition APIs. We select 3 most widely used ones: Microsoft Azure, Amazon Recognition, and Face++. For each of these APIs, we upload some cloaked image of a user X as a training data, and use the API to train a model and test whether the result model is able to recognize uncloaked image of user X. Fawkes achieved 100% protection success rate against each of these APIs. This shows Fawkes is effective against state-of-art APIs without needing any information about the face recognition system the tracker has used. We also explore many different challenging real-world scenarios. The first scenario we consider is when tracker obtain a set of original image of the user. In many cases, we do not control all the image of ourselves online. Some could be posted from a public source or posted by our friends. In this scenario, Fawkes remains successful when the number of cloaked images outnumber that of uncloaked images, and we leverage Siebel account to improve their protection effectiveness. So for users who have a lot of images already online, one way to improve their protection is to release even more images of themselves, all cloaked, which balance out the ratio. We also consider different countermeasures that can be utilized by the tracker and show that Fawkes is robust against all of them. Here we only consider automated countermeasure because Fawkes is focused on preventing automated tracking of a large number of users. A tracker cannot spend much energy and resources per targeted user because it does not scale well. We also extensively discussed the limitation of Fawkes. It is hard to guarantee Fawkes will be successful against face recognition system built in the future. In addition, with our current limited understanding of companies like Clever.ai, Fawkes is only an early work in this space. Again, there are more details in the paper on each of these topics. Today, we present Fawkes, a first step to protect individuals from recognition by unauthorized and unaccountable face recognition systems. With this, I would love to end this presentation by pointing you to our project website. The website contains links to our source code, code binaries, and frequently asked questions. We welcome you to try it out and give us feedbacks. Thanks for listening to our presentation. Emily and I would love to answer any questions.